Okay, might as well get started. I know some people aren't going to be here today, so chapter 16 homework is due on the 14th. The chapter 16 quiz is on the 12th. Your test grades are up on Blackboard. In general, on average, people did better than the last test. Your scores are better than the last test with a smaller curve, so in general. On average. So, yeah, that's what I'm gonna say. So we were talking about Mars. So Mars is a red color as viewed from Earth because the dust on Mars is heavy in iron oxide. So it's red, rusty. So it was named for the Roman god of war. The surface of Mars has two outstanding features that have intrigued scientists for decades: polar ice caps and extinct volcanoes. The ice caps are composed of solid CO2 in the winter and CO2 vapor with frozen water in the summer. So there's a permanent water ice cap and a seasonal carbon dioxide ice cap. That's how it works. And the red color is thought to be due to fine-grained iron oxide materials. Was associated with blood. Amusingly, oxidized iron is also why your blood is red. So some bits of Mars exploration. Mars is the most explored other planet. In 1997, pictures of the Martian surface were sent to Earth from a mobile radio-controlled rover, the Sojourner. In 2004, Spirit and Opportunity landed on opposite sides of the planet and confirmed Mars once had water on its surface. In 2005, the Mars Reconnaissance Orbiter was launched. Subsurface ice was found and the amount of water in the polar ice caps was calculated. In 2012, the Curiosity rover carrying a mobile lab landed. The goal is to see whether conditions have been suitable for microbial life and to search for past life. No life has been detected, but scientists are still working. And in 2021, the Perseverance rover with the Ingenuity helicopter landed. There's some recent thing about life on Mars, but I'm staying conservative about it at the moment. Curiosity landed in 2012 and Perseverance in 2021. These are rovers currently exploring Mars. They look more or less like this. This is Curiosity, but Perseverance looks very similar. And Ingenuity was a helicopter able to fly in Mars's atmosphere until it landed badly and shattered its blades. So here is a video about the Curiosity landing. Oh, yeah, oops. I have the wrong sound setting. Just a second. No.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
So that was the plan for Curiosity, basically. This is the actual landing for Perseverance, which is same process.
We're starting
more or
the
less.
straighten up and fly right maneuver, where the spacecraft will jettison the
We're
entry
able to put a
balance
bunch of
masses
cameras on
in preparation
Perseverance.
for parachute deploy and to roll over to give the radar a better look at the ground.
Applicant indicate chute deployed.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here in safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
And in fact, it looks like in a paper that was just published this September, Perseverance may have found evidence of past life. Well, they found what is because they are deliberately extremely conservative about that. They found something that is what is a possible biosignature in terminology used. They found something that on Earth would have been created by living things. They found it's in a rock. But it is possible for it to have been created in another way. So one of the things that's happening is one of the things that Perseverance can do is it can basically package up samples for a later mission to pick up and send back to Earth. So that's one of the things they're doing, is they're collecting a sample for the mission that will be sent pretty soon, I think. That should pack it up and send it to Earth Labs where they can do more detailed analysis. Because you're limited in what you can fit on a rover for your tools. So basically they found some deposits in rock that could be things made by like microbes. And if we found them on Earth, we would expect them to have been. But it is theoretically possible for them to have been created in things without life. So we have to put the possible biosignature thing. We don't have quite enough evidence to say life. But best evidence we've had so far, very strong, but NASA is deliberately extremely conservative about saying life exists. And this is a video of Ingenuity flying. So there's the helicopter taking off. Flying to the side. And coming back. And Ingenuity was a surprisingly successful, it crashed on flight 69 of 5. Because it was just a test bed to show that, you know, we could make a helicopter. And they were getting to the point where they probably would have had to abandon it anyways, even if it hadn't crashed, because it was getting too far away from the rover. Because it's hard to keep it up with the rover. So that's part of the issue. But yeah, it landed badly and shattered its blades. So the largest known volcano in the solar system is Mount Olympus on Mars. It's about 24 kilometers in height, about 3 times the height of Mount Everest. This is possible for a couple of reasons. On Mars, volcanoes are hotspot volcanoes. So they're always just, but there's no plate movement on Mars. So they can just build up higher and higher and higher. And the gravity is less. So the theoretical maximum height before the mountains start squooshing out sideways under their own weight is also higher. So here is a video about Mars.
To the ancient Romans, the planet Mars was symbolic of blood and war. But to many people today, the red planet may hold the key for a bright new future for humanity. The story of Mars began about 4.5 billion years ago when gas and dust swirled together to form the 4th planet from the Sun. Mars is the 2nd smallest planet in the solar system, with a diameter just shy of the width of Africa. In fact, its entire surface area is similar to that of all of Earth's continents combined. Much like its terrestrial cousin, Mars is dense and has a rocky composition. At the center of the planet is a core made of iron, nickel, and sulfur, which may have created a protective magnetic field during Mars's earlier years. Enveloping the core is a rocky mantle made of silicate minerals and a crust rich in iron. These iron minerals react with the trace amounts of oxygen in Mars's atmosphere and rusts, giving the planet its signature reddish hue. While its blood-like appearance inspired the ancient Romans to name Mars after their god of war, the planet's rusty color could be considered symbolic of the planet's prime days long past. Today, Mars is dry, desolate, and cold, with temperatures dropping as low as negative 225 degrees Fahrenheit. But billions of years ago, the planet was much warmer, more geologically active, and had a watery surface. Lake beds and river valleys snake along the face of Mars, indicating that liquid water was, for a time, present. Volcanoes, such as Olympus Mons, the largest volcano in the solar system at 3 times the height of Mount Everest, once erupted lava. But by about 50 million years ago, soon after Earth's dinosaurs died out, Mars's volcanoes also went extinct. Water on the red planet still exists today, but mostly in the form of polar ice caps. Because of factors such as the presence of water, some scientists believe life may have existed on the red planet and may exist again. Since the 1960s, space programs from around the world have launched missions to Mars in attempts to understand the planet's past, present, and potential for sustaining life. Life on another planet may well be out of reach for the near future. But if any planet can give us hope, Mars may hold the key to the survival of humanity.
Mars at closest approach. This is the Valles Marineris, which is a massive canyon on Mars. It's 4,000 kilometers long and 6 kilometers deep. And this is thought to be a crustal fracture caused by internal forces, causing the crust to tear. There's a nearby big bulge in the crust, so it may be tied to that. This is an image from Curiosity on Mars, imaging the surface. So those were the terrestrial planets. Moving on to the Jovian planets. The Jovian planets, Jupiter, Saturn, Uranus, and Neptune, are all much larger than the terrestrial planets. They are composed mainly of hydrogen and helium. The 4 Jovian planets have a very low average density, about 1.2 grams per cubic centimeter. And in fact, Saturn is less dense than water. What happened with the Jovian planets is because they formed further from the sun, it was cold enough for ices to condense, which allowed them to get bigger. And once they got big enough, they could start grabbing gases, hydrogen and helium, which are the most common materials in the universe. So if you grab them, there was a lot of them around, they could really get big. All 4 are thought to have a rocky core composed of iron and silicates. And then primarily in Uranus and Neptune, thick layers of frozen methane, ammonia, and water are found above the core. While Jupiter and Saturn have metallic hydrogen layers. So the formation of the terrestrial planets probably do have layers of methane, ammonia, and water as well. The terrestrial planets, the 2 least massive elements, hydrogen and helium, were most abundant when the planets started to coalesce about 5 billion years ago. And due to the heat from the sun, most of these less massive elements escape the gravitational pull of the inner planets. What could condense in that warmer area was heavier things, rock and metal. While further out, ices could condense, lighter ices could condense, which there were more of, and those could make bigger planets. The 4 outer planets were much further from the sun, therefore much colder, and so the Jovian planets retain much of their hydrogen and helium, which now surround their ice layers and innermost rocky cores. As a consequence, they have a much lower average density. They're mostly made of gas. So Jupiter is the largest planet in the solar system in both volume and total mass. Neglecting the sun, it's almost half of the remaining matter in the solar system. Named after the supreme Roman god of the heavens because of its brightness and giant size. Its diameter is about 11 times that of Earth's, and it's 318 times more massive than Earth. Its average density is significantly less than Earth's. It's about 1.3 grams per cubic centimeter. And it's covered with a thin layer of clouds composed of hydrogen, helium, methane, ammonia, and several other substances. So the outer atmosphere is hydrogen and helium. There are methane, ammonia, and other things in clouds. And it is the fastest rotating planet. It only takes about 10 hours to rotate. Generally, the bigger planets rotate. The larger planets rotate faster because there was more stuff to spin up, kind of idea. But yes, it's the fastest of the planets, rotation-wise. The terrestrial planets rotate more slowly. The Jovian planets rotate more quickly. So here's an image of Jupiter. You can see these bands. These correspond to, these are similar to the bands you get from in weather. You know, those convection cells we talked about when we talked about the weather. How Earth has like 3 convection cells. Well, Jupiter has more because it's spinning faster and it's bigger. And that's what you're seeing with these bands. There's the Great Red Spot, which is a giant cyclonic storm that has been running for centuries. It's been going so long that we don't have any idea how long it's been going because it has existed for as long as we've been able to see it. The Great Red Spot is this massive storm. It has erratic movement, shape, color, and size. Sometimes it seems to even disappear. It's a counterclockwise hurricane-like storm that's lasted hundreds of years. It has been shrinking, it seems, but we don't know if it's going to eventually go away or what. And here's a video about Jupiter. Another good image of the Great Red Spot there.
Born from primordial stardust 4.5 billion years ago, Jupiter was the solar system's first planet. And much like its namesake, the king of the ancient Roman gods, Jupiter was destined for greatness. Jupiter is the fifth planet from the Sun and the largest planet in the solar system. At approximately 11 Earths wide, Jupiter has twice the amount of mass as the other planets put together. But unlike Earth and the 3 other terrestrial worlds, Jupiter has no solid surface. It may not even have a traditionally solid core. Rather, this giant planet may have a dense liquid center surrounded by a worldwide ocean of hydrogen and helium gases. Jupiter's gaseous composition can be observed in its atmosphere. About 44 miles thick, the atmosphere is a canvas of stripes and storms churning across the giant planet. Their colors range between shades of whites, yellows, browns, and reds, all caused by the different chemical makeup of each area. Probably the most iconic feature of Jupiter is a crimson-brown storm that's been raging for over 300 years, the Great Red Spot. It's a giant swirling collection of clouds with wind speeds of up to 400 miles per hour, at least 2.5 times faster than Category 5 hurricanes. Floating hundreds of miles above the storms of Jupiter are about 79 moons, the most of the 8 known planets. The 4 largest moons were discovered by Galileo in 1610. Called the Galilean satellites, they include Io, the most volcanically active celestial body in the solar system, Ganymede, the solar system's largest moon, even larger than the planet Mercury, and Callisto and Europa, which, along with Ganymede, may contain oceans of liquid water underneath their crusts. Jupiter's large collection of moons is only made possible by the planet's massive size and gravitational pull, the strongest of all the planets in the solar system. This incredible gravity also influenced the sizes of the 7 other planets. During the solar system's earliest days, Jupiter, being the first planet to form, attracted and destroyed space debris that would have helped the other planets grow in size. Today, that force may serve as a shield by attracting comets and asteroids onto Jupiter's own surface, preventing them from crashing onto inner planets like Earth. Apart from the Sun, Jupiter has become the dominant figure in the solar system, thereby earning its place at the top of the planetary heap as king.
So Saturn has this distinctive system of 3 prominent rings and a couple more. It's got 6 rings that are defined. So 3 more not so prominent rings. And the rings and the planet are inclined about 27 degrees to the orbital plane. So that means what we can see of them changes as our angle on Saturn changes, basically. The rings are thought to be composed of ice and ice-coated rocks, ranging from around micrometers to about 10 meters. Saturn has the most moons of any of the planets, not Jupiter. The number they gave for Jupiter is out of date. It's like 90 odd for Jupiter. And just as of recently, they updated the number of Saturns, like 270 for Saturn. Saturn has a ridiculous number of moons. The most spectacular site, the rings are thought to be composed of ice and ice-coated rocks. The most spectacular site that can be viewed from Earth with a small telescope. It's really impressive to see, and it doesn't take a very big telescope. The diameter is about 9 times that of Earth, and it's got 95 times more mass than the Earth, and it's the least dense planet. It's only about 0.7 grams per cubic centimeter. And it's a lot less interesting. The atmosphere is less varied than Jupiter's, because the weaker gravity and thicker atmosphere means the cloud layers are thicker, so you see less variation. Because on Jupiter, you're looking at different colors or different layers of clouds, basically. And, they're being pushed up or pulled down, so they're more interrupted. On Saturn, those layers are thicker, so you just see that one layer. And so it's less interesting there, but it has the really dramatic rings. It has the most impressive rings of any of the planets in the solar system. So
with its gold color and stunning rings, Saturn is quite a planetary gem. Saturn is the second largest of the 8 planets, and it is about 10 times as wide as Earth. Despite its size, Saturn is actually the lightest planet. It is predominantly made of the gases hydrogen and helium, and because of its particular gaseous composition, Saturn is the only planet in the solar system that's less dense than water. If the planet were placed on an enormous ocean, it would be able to float. Saturn's gaseous makeup also means that it has no true surface. At its center, the planet has a dense core of water, ice, and rocky material, but it has no actual landmass. Instead, it's mostly made of gases, liquids, and yellow ammonia crystals that swirl around the planet, creating golden clouds and storms. The largest storm on Saturn is at its North Pole. It's over twice the size of Earth and shaped in a near-perfect hexagon. Each of the 6 sides is believed to be the result of jet streams, which all encircle a massive hurricane. Because of Saturn's inhospitable environment, the planet cannot support life, but some of its moons might. Saturn has more than 50 confirmed moons, and each varies in size and terrain. Enceladus, one of Saturn's smallest moons, is covered in ice and only about as wide as the state of Pennsylvania. Titan, Saturn's largest moon, is nearly as wide as Canada. Titan is also the only moon in the solar system with clouds and a dense atmosphere. Both Titan and Enceladus have underground oceans that would make them potentially capable of sustaining life. Saturn's moons may also play a role in shaping the planet's signature feature, its rings. Saturn's ring system is the largest and most complex in the entire solar system. The rings are made of icy and rocky remnants from comets, asteroids, and moons. The particles range in size from being as small as dust to as big as mountains. The ring system is divided into 7 groups of rings. Altogether, they are as wide as 4.5 Earths, but only about 2/3 of a mile thick. How the rings are able to stay on track and intact has to do with Saturn's smallest moons. Called shepherding moons, these tiny satellites orbit between the rings, and they seem to use their gravity to shape the ring material into circular paths. Saturn has fascinated scientists and amateur astronomers alike for thousands of years. The ancient Greeks and Romans, who named the planet after their god of agriculture, believed it was a star. It wasn't until the 17th century, after the telescope was invented, that scientists like Galileo Galilei, Christian Huygens, and Giovanni Cassini could take a much closer look. Only then was Saturn's planetary status discovered, and ultimately its many moons and brilliant rings. Because of its planet-like moons, lightweight composition, and dazzling ring system, Saturn continues to mesmerize us to this day.
There were a couple of facts in there that were out of date. Saturn currently has 274 known moons as of March this year, when they added like 150. They discovered more. Yeah, they found them. So part of it is that Saturn has had orbiters around it, and that's how they've been finding these moons. So they found more. They're not big moons, they're little ones. And Jupiter has 97. I was just looking these up. But yeah, no, they just recently added a whole bunch. So a moon is defined as a naturally occurring orbiting satellite of a planet. And it needs to have like a stable orbit, and it's not gonna, fly away. So even though, Earth currently has a couple objects that are acting sort of moonish, orbiting it, but their orbits aren't long-term stable. So I think that's how they determine it. I don't know exactly, because these definitions are all a little fuzzy, but there has to be something for size, because I mean those rings are made of thousands of little specks, but I don't know the exact line they draw, but that's part of it. And then so Saturn has the most impressive rings of any of the outer planets. They all have ring systems, but Saturn's are the only ones that are like big and obvious. And they're fed by material from the moons and such stuff like that. So they probably haven't been around that. Saturn's rings are probably not actually all that old in geologic time, and are probably not going to last forever. But here is Saturn and its rings. Here's a view from the far side, where Earth is here, Venus is here, Mars is here. The next planet is Uranus, which was discovered in 1781 by William Herschel, who was an English astronomer. It was named after Uranus, the father of the Titans and the grandfather of Jupiter. Saturn is Jupiter's father. Uranus is Saturn's father. They're just sort of moving along. They didn't continue that pattern for the next one because they ran out of fathers. Uranus didn't have a father. Because mythology be like that sometimes. It has a thin ring system composed of, say, boulder-sized particles that are quite dark, so they're hard to see, with very little dust. Its average density is only about 1.3 grams per cubic centimeter. And the biggest weird thing about Uranus, it rotates on its side. It has the biggest axial tilt of any of the planets, at about 90 degrees. The thought is that it was probably a collision early in the history of the solar system that knocked it on its side, especially because all of its associated stuff, like rings and moons, also orbit more or less with that tilt. So it's probably some sort of early collision. That just tilted it over, basically. Similar as thought, the reason why Venus rotates very slowly backwards is a large collision early on as well. So we know big collisions happen. Like, for example, it's our only good explanation for our moon. And we find giant craters on certain planets. Like the northern end of Mars is kind of a giant crater. I think it's the northern end, but yeah. There was a lot of stuff around that could wang into stuff early on in the solar system when planets were still forming. So big collision probably knocked it on its side. Oops. YouTube videos don't play.
In ancient times, humans studied the night sky and discovered the worlds of Mercury, Venus, Mars, Jupiter, and Saturn. But beyond this realm of knowledge, another world shined brightly, just waiting to be discovered. Uranus is the 7th planet from the Sun. From a distance of about 20 astronomical units, or 20 times the distance between Earth and the Sun, Uranus orbits the star once every 84 Earth years, approximately the length of a human's entire life. This orbit causes each season of Uranus to last that much longer. Theoretically, a human living on Uranus would experience the 4 seasons only once, but each for about 21 years. Partially due to its distance from the Sun, Uranus boasts the coldest temperatures in the solar system. These icy temperatures, dropping as low as -370 degrees Fahrenheit, are largely influenced by the planet's composition. At about 4 Earths wide, Uranus has an Earth-sized core made of iron and magnesium silicate. The remainder, approximately 80% of Uranus, is a worldwide ocean of ices made of water, ammonia, and methane, the chemical behind the planet's cool blue color. This icy composition prevents Uranus from emitting much heat compared to other planets, making the blue world the solar system's coldest. In addition to its extreme temperatures and orbit, Uranus has a dramatic orientation. While the other 7 planets spin on their axes like tops, Uranus appears to roll along its equator. The planet is tilted at a near right angle, in which polar regions point toward and away from the Sun rather than upward and downward. This tilt, thought to be the result of Uranus's collision with at least one celestial body, has also affected the orientation of Uranus's 13 rings and 27 known moons. Unlike the rings and moons of other worlds, which orbit their home planets horizontally, those of Uranus orbit in a vertical orientation along the planet's tilted equator, much like a Ferris wheel. Uranus and its many unusual features were a mystery to the ancients, and the planet was actually thought to be a star. But in the late 18th century, astronomer William Herschel discovered that the celestial object was actually a new world. The scientific community debated over what the planet should be called, and eventually chose a name suggested by astronomer Johann Elert Bode. Bode believed that since Jupiter was the father of the gods, and Saturn was the father of Jupiter, then this new planet should be the father of Saturn, Silus. But rather than following the tradition of using names from ancient Roman religion, Bode instead opted for Silus's ancient Greek equivalent, Uranos. Uranos, the ancient Greek god of the heavens, was then Latinized to be Uranus. To this day, Uranus is still the only planet that veered from tradition with an ancient Greek namesake, a status most fitting for a planet beyond convention.
It also has an exception in the way its moons are named. It has 29 known moons, of which 27 are named. But Uranus's moons are named after characters from Shakespeare plays instead of various minor Greek deities and such. Greek or Roman deities. So it revolves around the sun on its side, and it technically rotates in a retrograde fashion because it's tilted 97 degrees or something like that. But it's basically on its side. The last of the planets is Neptune, which was discovered in 1846 by Johann Galle, a German astronomer. And the Englishman John Couch Adams and the Frenchman U.J. Leverrier were mathematicians using Newton's law of gravitation. And they noticed that the orbit of Uranus was disturbed. And they predicted the location of another planet from those disturbances. And that was how Galileo eventually discovered Neptune. And a similar process where they're looking at orbits and seeing where things are disturbed. That is why people think there might be another planet out way far away in the Kuiper Belt. Neptune also has a large dark spot similar to Jupiter's. It's thought to be the result of a large wind system that has gone away at this point. So that storm is probably over. Neptune and Uranus are similar in size and the composition of their atmospheres. And in many respects, these two planets can be considered twins. Neptune and Uranus are very similar to each other. And Jupiter and Saturn are similar to each other. So here's a video on Neptune. And it has like 14 known moons. We just haven't visited Neptune.
Along the dark edges of the solar system, it floats. Anchored by a star, but barely graced by its warmth, this traveler drifts alone, as deceptively calm and elusive as the deep blue sea. Neptune is the 8th planet from the Sun. At about 30 times the distance between our star and the Earth, or 30 astronomical units, Neptune is the most distant planet in our solar system. This distance creates the longest orbit of the 8 worlds, about 165 years, with the seasons lasting a little over 40 Earth years each. Being so far away from the heat and light of the Sun, Neptune is cold, dark, and icy. At its heart is a solid core about 1.5 times the size of Earth. Making up about 45% of the planet's mass, the core is made of water ice and silicate rock. The rest of the planet is believed to be a hot, pressurized ocean of water, methane, and ammonia ices surrounded by a layer of clouds. These clouds, predominantly made of hydrogen and helium, include traces of methane, which give this ocean world its rich blue color. While the clouds create a cool, calm veneer from afar, up close they are whipped around by the most severe weather in the solar system. Winds on the planet reach speeds of over 1,200 miles per hour, nearly 5 times faster than the strongest winds recorded on Earth. In fact, the winds are so powerful that they break the sound barrier. Drifting high above this windy ice front is a quiet ecosystem of rings and satellites. 6 rings encircle the planet, with some containing ring arcs, or clusters of dust particles in a ring. Also revolving around the planet are 14 known moons, with the largest called Triton. Named after the son of the ancient Greek sea god, Triton has ice volcanoes and may even contain a subsurface ocean. Much is left to be discovered about Neptune, its rings, and its moons. Only one spacecraft, Voyager 2, has visited these cosmic bodies, but future missions to this mysterious, icy world would have even more stories to tell.
So Neptune Like Uranus, it is very blue. That's from the methane in the atmosphere. And in 2006, so those are the major planets of the solar system. The International Astronomical Union adopted the following criteria for a solar system body to be a planet. What was a planet? There was not a fixed definition of a planet until 2006. So the criteria are as follows. It needs to be in orbit around the sun. It can't be a moon of another planet. It needs to be big enough for self-gravity to form a nearly round shape. So it needs to be big enough to pull itself into a ball, basically. And it must be the dominant body within its orbit. This is a little fuzzily defined. There's still a lot of debate about how to officially define dominant body in its orbit. But the general idea is that it needs to be the primary thing in its orbit that not, there's not like other stuff in there. It's not sharing it with a bunch of other stuff. This is to sort of differentiate from like asteroids and Kuiper belt objects. And it's this last statement that Pluto fails. So basically, Pluto is in orbit around the sun. It has enough mass for self-gravity to form it into a nearly round shape, but it is not the dominant body in its orbit. If you add up all the other stuff in Pluto's orbit, it's about 13 times the mass of Pluto. If you do the same thing for the Earth, it's a couple percent. It's a few percent. Yeah, that's sort of the difference we're looking at. So the simplest thing you could say is that Pluto's orbit takes it inside that of Neptune, so it's not the dominant body of its orbit. But this is similarly true for other stuff that's orbiting, where there's a lot of other stuff there. So the IAU established two new categories for objects that orbit the sun. These were dwarf planets and minor planets. Dwarf planets are things that meet the first two criteria, but fail the third one. So there are 5 official dwarf planets, and there are like at least half a dozen more likely dwarf planets out there that haven't been made official by the IAU. So the official dwarf planets that are now designated by the International Astronomical Union are Pluto, Ceres, Eris, Haumea, and Makemake. So Pluto is Pluto. It's the nearest large object in the Kuiper belt. Ceres is the biggest object in the asteroid belt. It's big enough to make itself round, and was thought to be a planet at one point, and then they realized it was an asteroid. So this is the same thing happening with the Kuiper belt. And Eris is the reason that Pluto is not a planet anymore. So Eris is another object out in the Kuiper belt that is similar in size to Pluto, about 25% more massive, and also out there. So if Pluto was a planet, Eris would also have to be a planet. And they were starting to find, they'd also found Haumea and Makemake, which are a little smaller and further out. And they're starting to go, okay, so we found this new category of stuff out in the Kuiper belt. They don't really work as planets. So we defined stuff orbiting in the sun. We made some new categories. Major planets are planets. Meet those 3 criteria. If you meet the first 2, you're a dwarf planet. And if you're only just a thing orbiting the sun, you're a minor planet. And it's just a classification system. So here is a video about how Pluto went from planet to dwarf planet, and how it's not that big a deal. Other than now we have a nice...
You may have noticed that we now have only 8 planets in our solar system. Most of us grew up with 9. Pluto was the 9th, but it's no longer a planet. I'll explain why not, and also, if Pluto is no longer a planet, just what is it? Pluto was discovered back in 1930 and added to the list of planets. Its orbit is a strange one, taking it for a time closer to the Sun than Neptune. But more of its time is spent beyond Neptune, all by itself. At least we thought it was by itself. In the early 1990s, two smaller objects were found in orbits near Pluto's, in what is now called the Kuiper Belt. These discoveries were followed by more objects in the Kuiper Belt, all smaller in dimensions and less massive than Pluto. But even then, some astronomers questioned if Pluto should be considered just another Kuiper Belt object instead of a planet. And this wasn't the first time something like this had happened. In 1801, a new object was discovered orbiting between Mars and Jupiter. It was given the name Ceres. During the early 1800s, Ceres, along with its neighbors Pallas, Juno, and Vesta, were considered planets. But that changed with the discovery after 1845 of many more of what are now called asteroids, also orbiting between Mars and Jupiter. After that, Ceres and the rest were reclassified from planets to asteroids in what is now called the asteroid belt. So it was natural that many would question whether Pluto should still be called a planet, given that many more objects were found around its orbit. Pluto's status as a planet was then put under even more pressure in January 2005 when Eris was discovered in the Kuiper Belt. Eris is practically the same diameter as Pluto, but its mass is around 25% more due to its higher density. The discovery of this more massive object alongside Pluto meant that either Eris should be added to the list of planets, or Pluto should be reclassified to something else. In 2006, the International Astronomical Union, the IAU, convened to decide just what the definition of a planet should be. The final decision was that a planet should meet three criteria. 1. The planet is in orbit around the Sun. Check. Pluto orbits the Sun. 2. The planet has sufficient mass for its own gravity to pull it into a nearly round shape. Check. Pluto's gravity has made it nearly round. And 3. The planet has cleared the neighborhood around its orbit. This is done either through collisions or redirecting objects away. And this is where Pluto fails. Pluto accounts for only a small fraction of the mass around its orbit. To put this into perspective, there are thousands of relatively small asteroids, called near-Earth objects, around Earth's orbit. But the Earth's mass is 1.7 million times the rest of the mass in its orbit. On the other hand, you'd need around 14 Plutos to equal the mass of everything else in its orbit. So if Pluto isn't a planet anymore, what is it? At the same meeting of the IAU, a new classification was formalized, called a dwarf planet. What's a dwarf planet? A dwarf planet is one that meets the same first two criteria for a planet, but has not cleared the neighborhood around its orbit, just as Pluto hasn't. Plus a fourth criteria. A dwarf planet is not a satellite, like our moon is a satellite of the Earth. Check. Pluto isn't a satellite of any other object, other than the Sun, that is. So Pluto is a dwarf planet, and so are Ceres and Eris. As of now, there are only a handful of dwarf planets, but it's suspected that there may be up to 200 in the Kuiper Belt, and maybe even more than 10,000 when objects outside the belt are considered. This video was made as a collaboration with All Time Numbers. Check out this stunningly awesome video of theirs, The Universe in Numbers, by clicking on this preview or on their logo to go to their channel.
Discover the universe in numbers. The diameter of the observable universe is 28 billion parsecs.
So, and there are other things that are generally considered dwarf planets, but haven't gone through this. There's a whole lot of debate here. The whole thing is still actively discussed, but there's like 4 more that are generally considered planets by their mass and such. Quasar, Sedna, Orcus, and Gong. And then that's one more that's often considered. I believe it was Salacia. But yeah, so those are various dwarf planets. So Pluto is the second dwarf planet from the Sun beyond Neptune, because the first one is in the asteroid belt, it's Ceres. It's named for the god of outer darkness. Pluto and Ceres are the only dwarf planets to have been visited by spacecraft. Its average density is only, the god of outer darkness, god of the underworld. Its average density is 1.65 grams per cubic centimeter. It was discovered in 1930 by C.W. Tombaugh, who was investigating apparent discrepancies in the orbital path of Neptune and Uranus. It doesn't resemble either the terrestrial or the Jovian planets. It's quite different. It's much less dense than terrestrials and much smaller than any of the other planets. And it has not been made, well, it had a flyby by the New Horizons spacecraft. It hasn't been orbited by a space probe. There's nothing that's landed. But in 2015, the New Horizons spacecraft flew by it. We couldn't, for practical reasons, it's basically impossible to get a spacecraft out to Pluto and have it stop. You have to go so fast to get there that you kind of can't stop. And Pluto is so small that you can't really use its gravity very easily to slow down. But it got detailed imaging by New Horizons where we learned a whole lot, actually. So here's the solar system. You can see that Pluto's orbit is greatly inclined compared to the others. Venus, Earth, Mars, Jupiter, Saturn, Neptune, Uranus. And the outermost reaches of the solar system, there's the Kuiper Belt, which extends from just beyond the orbit of Neptune and out quite a ways, where there's also Eris out in there. And it consists of comet and cometary materials and other small objects, which are generally classified as trans-Neptunian objects. And many astronomers put the edge of the solar system to be at about 100 AU. And Voyager 1, launched in 1977, and in 2004 reached 100 AU, approximately 93 billion miles from the sun. And in 2013, it was confirmed it had reached interstellar space and beyond the region dominated by the sun's magnetic field and the solar wind. There's like actually a transition where, the sun's solar wind is impacting with the winds from other stars and sort of the intergalactic wind. And both Voyager 1 and Voyager 2 have passed that point at this point. So I can look up the locations because there's like an automatically updating thing from NASA that tells you how far away they are. So currently Voyager 1 is 169.5 AU from Earth, and Voyager 2 is 141.2 AU from Earth. And they're both flying away into interstellar space. So let's talk about the origin of the solar system. So any theory that purports to explain the origin and development of our solar system needs to account for how it is now, its present form. According to our best measurements, our solar system's been in its present state for about 4.5 billion years. And any valid theory for solar system formation has to be able to explain a number of major properties of our solar system. Where did the material come from? What were the forces that formed the solar system? Why do we have isolated planets in circular orbits, all in the same plane, all orbiting in the same direction? Why do they all orbit in the same direction? Why do most rotate in the same direction, with 2 exceptions? How do we explain those exceptions? Why do we have 2 types of planets, terrestrial versus Jovian? Where did the asteroids come from? Where did the comets and meteoroids come from? So the general idea is that the solar system began with a large swirling volume of cold gas and dust, a rotating solar nebula, which collapsed under the influence of its own gravity. Most of the mass formed into the sun, but some of it spun out into a flattened rotating disk, and further contraction produced the proto-sun, and that disk accreted to form the planets and all the other stuff orbiting in the plane of the solar system, while some remaining stuff is on more random orbits. And as particles moved inwards, the rotation of the mass had to increase to conserve angular momentum, like an ice skater bringing in their arms, and so they span up faster and faster. So this is known as condensation theory or the nebular hypothesis.
Formation of the planets. The universe comprises countless galaxies, each one containing numerous stars. Around some of those stars, there are planets, just like those that orbit our own star, the Sun. The nebular hypothesis is the most widely accepted explanation for how the Sun and planets in the solar system may have formed. When our solar system was first created, all that was thought to have existed was a cold, spinning cloud of gas called the solar nebula. The nebula resulted from an uneven distribution of gases throughout the universe. As the gravitational pull began to condense the gas toward the center, the speed of the rotation increased. This caused the cloud to flatten, creating an accretion disk. Matter continued to collect as the growing force of gravity drew it toward the center. Eventually, the gas warmed from the increasing pressure. As the mass further increased, the gravity also increased, and as a result, the temperature continued to rise. A ball of hot gas formed in the center of the accretion disk, creating a protostar, also known as the Sun. Finally, when enough gas gathered in the center of the protostar, the pressure generated enough heat to fuse the atoms, forming a star. Outside the star, matter was forming into clumps of gas, dust, and rock, which created protoplanets. These protoplanets continued to grow as they trapped material in their gravitational fields. Because the protoplanets all formed from the same cloud of gas and dust, they travel around the Sun in the same direction and in the same plane. The nebular hypothesis also explains how the planets are arranged. The heat and solar winds caused by the Sun swept the lighter gases farther out into the developing solar system. This is why the rocky terrestrial planets, Mercury, Venus, Earth, and Mars, are located closer to the Sun. The gas giants, Jupiter, Saturn, Uranus, and Neptune, formed in the cooler outer region of the solar system. The solar system continued to evolve even after its initial formation. Large asteroids slammed into planets, and the planets themselves differentiated into layers as they slowly cooled. Although the nebular hypothesis cannot be directly tested, it is a useful description for how a solar system forms. It explains why planets and the star they orbit usually spin in the same direction and lie in the same plane. It also explains the arrangement of the planets, with the rocky planets nearest to the Sun and the gas giants farther away. The next time that you look at the stars twinkling in the night sky, imagine new planets forming using these very steps.
So this is the condensation theory and the nebula hypothesis. You have the nebula, it collapses, and then the material that's spinning, most of the material forms the Sun in the center, and the remaining material that's sort of in a disk around it condenses into planets. So the Sun and the planets orbit the Earth in the geocentric model of the solar system. The Earth and the other planets orbit the Sun in the heliocentric model of the solar system. The orbits of the planets are generally in the shape of ellipses. The law of elliptical orbits was developed by the scientist Johannes Kepler. An astronomical unit represents the average distance of the Earth from the Sun. When a planet is closer to the Sun, its velocity is higher. When it's further, it's smaller. Velocity is lower. The point where the Earth is closest to the Sun is called perihelion. The point where Earth is furthest from the Sun is called aphelion. Planets with orbits smaller than Earth are called inferior. Planets with orbits greater than Earth are called superior. The planets revolve around the Sun in counterclockwise direction. All planets rotate counterclockwise except for Venus and Uranus. Non-gaseous planets are referred to as terrestrial planets. Gaseous planets are referred to as Jovian planets. Planet closest to the Sun with the shortest period of revolution is Mercury. The planet with a thick atmosphere of carbon dioxide is Venus. Has a thin atmosphere and appears red in color is Mars. Mars is has the largest volcano in the solar system. The gaseous planets are composed primarily of the elements hydrogen and helium. The largest planet is Jupiter, and it has the shortest period of rotation. The planet with the most prominent ring structure is Saturn. Uranus and Neptune have a blue tint due to the gas methane in their atmospheres. Pluto is classified as a dwarf planet, and the most current theory of the formation of the solar system approximately 4.5 billion years ago is the nebular hypothesis or condensation theory. And that is all for chapter 16. And that is it for today. Have a nice day. Your grades for the test are up on Blackboard. Yeah.